Hi everyone, I'm John Boprosky and welcome to my webinar on how to create a perfect receiver continuous time linear equalizer model from circuit data. Please type any questions into chat as I proceed with this webinar. I will have a questions and answers session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? Well, high-speed digital integrated circuits and serializer-deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or to own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations. This webinar is to let you know about the process I have used for many years to create perfect receiver CTLE models from circuit data. So what is SerDesDesign.com? I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to over 40 high-speed digital integrated circuit companies over the past 10 years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI modeling building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that the expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools: Microsoft Visual Studio, CMake, web browsers, HTML, JavaScript, PHP, C++, and more. I learned that creating an IBIS-AMI model should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct circuit simulation data and use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows PC. What will this webinar show you? It first gives you an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create perfect receiver CTLE models for use in IBIS-AMI models. I give a real-world example for an RxCTLE IBIS-AMI model generated from circuit simulation data. And finally, I show you how you can get a copy of my receiver CTLE model generation tool for use on your Windows PC. So, modeling a SerDes system in a channel simulator. Channel simulators are based on the IBIS OpenForm standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. This block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes systems include the following: the transmit IBIS-AMI portions, where the AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer, and the IBIS portion, which provides the differential output to the channel. There's the transmit package, the channel, the receive package. These pieces represent the differential channel. Each part is optional and may be represented using S-parameter files. There's the receiver IBIS-AMI portions. The AMI portion typically contains a receiver continuous time linear equalizer, a clock and data recovery unit, and a decision feedback equalizer. An IBIS portion has the differential input from the channel. So, modeling a SerDes system. A key channel simulator property to keep in mind is that it considers that the entire analog content, the green area in this figure, the total channel, between the transmit AMI portion and the receive AMI portion is linear and time invariant. As an LTI system, the entire differential analog section in this SerDes system is accurately represented by its single-ended impulse response. The key concept enables the channel simulator to achieve its fast simulation speeds. Creating a perfect receiver CTLE model from circuit data. IBISAMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I've used this process over the past 10 years, providing custom IBISAMI models to over 40 plus companies based on the circuit data they provide me. In today's webinar, I provide instructions on modeling and receive SerDes CTLE with circuit data. The modeling data is collected typically from a SPICE circuit simulator, and this discussion is for receive SerDes with a CTLE but no nonlinearity CDR or DFE. Modeling with the nonlinearity CDR or DFE is discussed in other SerDesDesign.com webinars. To start, let's talk about the typical SerDes system test points. This figure shows typical test points for a SerDes system. For the current discussion, test points TP0, TP4, and TP5 are used for data collection. A low-loss channel is assumed. NRZ data streams are used for modeling. TP0 is the NRZ waveform. The data collected at TP4 is the input impedance at the receiver input differential pins, the time domain waveforms at the receiver input differential pair. The data collected at TP5 is the time domain waveform data at the CTLE output. The receive circuit input impedance is measured at TP4. The receive SerDes differential input impedance is measured with an input load resistance of 50 ohms or per pin, that's 100 ohms total differential. The S2P parameter data with touchtone 1.0 format is collected at TP4 from 0 Hz to Fmax in steps of F-step, where Fmax is greater than or equal to 2 times the symbol rate and F-step is less than or equal to 10 megahertz. This data is collected for each receiver SerDes corner case. This data is used to create the receiver input IBIS buffer modeled as an S4P file based on the IBIS-AMI 7.0 specification or later. The receiver modeling data is collected at TP4 and TP5. The modeling data is collected in the time domain. Even if the system is using PAM4, the modeling signaling is NRZ. This NRZ waveform data is used to create the receiver AMI model and for NRZ verification. If PAM4 is used by the received SerDes, then additional waveform data may be collected using PAM4 signaling, and that waveform data is only used for PAM4 verification. The drive level into the received SerDes must be at a small signal level. It should be far from any input nonlinear compression level. The following pages discuss the data collection requirements. The receive input waveform. The receive SerDes input waveform data is collected at TP4 with the receive SerDes replaced with the load resistance RL for each corner case, where RL, the load resistance per pin, is based on the S2P data from the prior slide at 0 Hertz. Note that that resistance is based on the characterization resistance of the S parameter file, Z0, and the STD11 characteristic of the S parameter file. And use it with the defined corner case channel is assumed. The Rx output waveform data is collected at TP5 for each corner case. The drive level into the Rx SerDes input must be at a small signal level. This should be far from any input nonlinear compression level. And here are the waveform details. The figure represents a typical captured received SerDes waveform at TP4 and TP5. The bit rate is at the minimum bit rate where to be used by the system, and the waveform time step is no larger than the maximum bit rate over 32. 250 to 1,000 UIs of a PRBS pattern is captured. Within it, there must be a set of consecutive N0s and M1s, where N and M are large enough to allow for settling of the rising and falling waveforms. This waveform data is used for modeling purposes as well as for verification of the IBIS-AMI model. So here's a typical schematic used for data collection. Be sure that TP4 has a proper load resistance, which is based on the received circuit input S2P data at 0 Hertz. Be sure that the received circuit input level does not drive the RxCTLE into any nonlinear region, and collect the TP4 and TP5 data together into one data file for each CTLE state. Here's the waveform file details. There's one file for each received SerDes state. The output file is a text file with these columns. First column is for time. The second column is the NRZ waveform. The third column is the received SerDes input into properly terminated load resistance. And the fourth column is the received SerDes output. Use a file name that includes the received SerDes name, corner case name, and the names of any control parameters. Processing this data is discussed here on an overview basis. The received data collected in the prior slides is processed by the SerDes design tool, SerDes IBIS-AMI Received CTLE Data Processing Tool. This discussion is just to give you an overview of what will be done by SerDesDesign.com. The IBIS S2P data is converted to an appropriate S4P file and impulse response. This S4P file is used as the IBIS buffer. The set of waveform files are combined into one file. All files should use the same NRZ pattern. All file data is checked to have time values with monotonically increased time. And there will be 1 plus 3 K columns in the combined file, where K is the number of CTLE states. This combined file contains all the original data. The segment with the consecutive N0s and M1s is extracted from the combined file. The extracted Rx input waveform segment is convolved with the IBIS buffer impulse response. The modified receive input waveform segment is de-embedded from the extracted receive output waveform segment to form the receive step response waveforms. The receive step response waveforms are used in the AMI model. The IBIS-AMI model is based on the IBIS 7.0 specification or higher. Here, this block diagram summarizes the signal processing. HS represents the received circuit input to CTLE output transfer function. This is based on the CTLE input output waveforms. At small signal levels, this is assumed to be LTI. H1 of S represents the IBIS portion as derived from the S2P data. H2 of S represents the AMI portion as derived as discussed on the prior slides. And in the frequency domain, H2S is just equal to H1 of S times H2 of S. H2 of S is based on the HS data with the H1S response de-embedded. Converting the processed data into an IBIS-AMI model. For discussion in this report, this is considered to be linear in time invariant. So the receive IBIS-AMI model has an IBIS file that includes a model section with model type input. It has an IBIS circuit defined that is ignored because the one defined by the S4P file is used instead. The AMI file has reserved parameters that define the IBIS portion for an S4P file. So per the IBIS specification, there's a TS4 file parameter and an RxR parameter. And so using the IBIS-AMI model building project that's included in the SerDesDesign.com tool, use of this IBIS-AMI modeling builder tool is only dependent on the installation and use of the free Microsoft Visual Studio tool. See the instructions included with that tool. This project contains these folders and files. Only one CSV file and one S4P file generated from the prior steps are required for this IBIS-AMI model. So, for generating the IBIS-AMI model, Visual Studio is run on this project. Then the required IBIS-AMI files are generated. That includes the .ami file, the IBIS file, the S4P file, and the DLL, all used. Use of these of the SerDesDesign.com processing tool enables you to create any number of receive CTLE IBIS-AMI models with the same licensing limits of the tool. Use of the IBIS-AMI model on any Windows or Linux machine requires that the built-in licensing restrictions must be removed. To do this, send your AMI solution with any additional instructions to SerDesDesign.com, and IBIS-AMI model with licensing restrictions removed will be sent to you with your payment in the SerDesDesign.com store for an amount that is 50% of standard model pricing defined in the response received from SerDesDesign.com. So here's an example pricing. And here, let me go to a customer example. This example is based on work with Silicon Creations. Their example had this block diagram. The Rx IBIS-AMI model included CTLE, nonlinearity, CDR, and DFE, and it was generated using various tools from SerDesDesign.com. This webinar process that for discussion today was used to create the CTLE IBIS and AMI models. The CTLE has 32 states for each of 3 corner cases. Here's what Silicon Creations said. The feature-rich models were critical to our first pass success. The models delivered by John have been critical to our success. They easily supported customer integration of our SerDes IP. They fixed causality issues found in other channel simulations. And the SerDesDesign.com process uses 3 directories. One is a directory for the IBIS-AMI build. One directory contains the data processing tool, and one directory contains the circuit simulation files. The circuit simulation files include all these waveform data files at TP4 and TP5, as well as the S2P data file for the Rx circuit input impedance, as well as a file listing all the waveform data files. So in this case, the ADS waveform.tim files are assumed, but the file can be any text file. Just requires that there's be 4 columns, as was discussed: the time, the NRZ waveform, the waveform at TP4, and the waveform at TP5. So this tool has 1 executable, 1 batch file, and 1 file with user commands. So run this tool by selecting the batch file, and the command window displays for the start and end of the tool are shown to the right. The tool includes a template for creating the IBIS-AMI model. Just copy 2 files, 1 CSV and 1 S4P file to the CTLE directory, and the IBIS-AMI model generated results in perfect agreement between the model and data. So the circuit waveform data can be compared to the IBIS-AMI model output waveforms, given the same circuit input waveform. In all cases, all have perfect agreement. Here's a display of the CTLE with the minimum, intermediate, and max equalization. In summary, this webinar has shown you how to achieve a perfect data-based IBIS-AMI model for a received SerDes circuit with a CTLE. These steps were discussed. Convert the S4P data to an S4P file and its equivalent impulse response. combine the set of waveform files into one file, extract the desired waveform segment, de-embed the input waveform plus S4P impulse from the output waveform, and generate an IBIS-AMI model from the waveform data and S4P file. These steps are automated with the tool from SerDesDesign.com with the CTLE data processing tool. So I really want to introduce you to a personal copy of my SerDes IBIS-AMI Receive CTLE data processing tool. It's the same process I have used successfully with my customers over many years. It automates the use of circuit simulation data in one step, includes IBIS-AMI model building environment, automates the creation of unlimited number of Receive CTLE IBIS-AMI models. Here's what you get in the tool. It does the automatic conversion of the S4P to S4P data, S2P to S4P data. It automatically combines the circuit simulation waveform data files into one file. It automatically extracts the desired waveform segment. It automatically de-embeds the input waveform from the output waveform, automatically generates the receive IBIS-AMI model, and you can generate an unlimited number of IBIS-AMI models. It includes instructions and examples. It has licensing conditions. That's a time-based, node-locked license. It's available with a 12-month license for $1,500. And I'd like you to check it out on my dime. You know, I really guarantee that this will be very successful for you. You have a full 30 days to put it to the test. If at any point you don't feel that you're getting your money's worth, just contact me and I'll give you every penny of your investment back. I'll only want you as a customer if you're 100% happy with your investment. Simple as that. So you can purchase my tool and use it for a free month. Your 12-month license starts after your 1-month free trial. You can see ordering instructions at this web page and see the link below this webinar presentation as well. And this concludes my presentation for this webinar. I'll end the recording of this webinar and spend time with you to address your comments and questions. And you can also remember to email me any comments or questions at my email address, johnb@serdesdesign.com. Thank you much for attending.